Welcome back to the AS level physics series. We'll be continuing with the Newtonian mechanics 1 section, the chapter of kinematics, and today we'll be focusing on graphs. Now, graphs really is just a visual picture, and this visual picture helps you relate to variables in such a way that you can see how one of the variables changes with the other variable, right? So, for example, you could have a displacement versus time graph where you can see how displacement is one of the variables and how it changes with respect to time as time moves on. So we can use these graphs to see what happens as time progresses forward. Now, a graph really is, it could be a straight line. So an example, suppose that you have a graph. It is represented using some axes. So we have a horizontal axis and then you have a vertical axis. Now, normally in mathematically speaking, you can say that this is a y-axis and this is an x-axis. These are just the variables, letters associated to these axes. It doesn't mean really anything. You can assign any variable or any letter to these axes mathematically. However, if you're talking in terms of physics, we find it rather more convenient to define a variable such as time on the horizontal axis, while on the vertical axis it is convenient to define the variable which is changing with respect to this time. So a graph could be really a straight line or a curve as well, and it will give us a relationship between these two quantities. So maybe it could be something like this, or it could also be something that looks like this, or whatever, right? So you can have multiple options. Maybe something that looks like this, and maybe something that looks it could even be a line that is like this, and you could also have something that looks like this. Well, it's not really like this, but maybe something that looks like this, which is, it is really parallel to the y-axis. So you can have multiple options really, and so let's really begin our discussion with the displacement time graphs. So let's go a bit over here. So let's start with displacement time graphs. These are those graphs which will show you how does my displacement change with respect to time. So I can say that we have a relationship between displacement of the object to time. So if I look at a graph, let's look at a particular graph. We have on this axis we'll have displacement. You can denote it with S and the units are in meters, while on the horizontal axis, and this is very long, so let's just keep it till here, you have time, which is represented with T and is measured in seconds. Now just suppose that you have a line on this graph that starts from this center, which is origin, and it goes like this. Now it is starting from the origin. This is the origin point. At this origin, the coordinates are, for time it's 0, and displacement, as we can see, is also 0. Now you can see that this graph is really showing you the displacement of any body which is increasing at a constant rate uniformly with time. As time progresses, it increases at a constant rate. The constancy is determined because it's a straight line graph. There is no curves in this graph. So curves imply non-uniformity, right? While the straight lines are constancy. Now, the gradient of this graph is defined as the displacement divided by time. So mathematically speaking, the gradient of a graph can be found by taking any 2 points on this line. So I take this one, and maybe suppose you take 0, 0, because the line passes through that point. So this could be some value x2, we'll use a t, so this would be t2 and s2, while this could be some other some value. Let's suppose that this is just some t1 and s1. Now we know from mathematics that the gradient of a graph is given as it's normally represented with m, right? So you can see that it is the change in the vertical axis, which is s, divided by the change in the horizontal axis with it, which is this thing, delta t. Now this thing is really s2 minus s1 divided by t2 minus t1, but we know what is this thing, what is this change in displacement divided by time. This thing is simply velocity. So which means that the gradient of a displacement time graph is going to give you velocity of the object. Now it's just a hint, or you can say a piece of advice at this point, that whenever you're measuring a gradient of a graph, make sure to use as much of the graph as possible, because when you do that, that will reduce the percentage error in your calculations. So by that, what I mean really is that if you have use more points, right, or really if you pick a point t2 and s2 over here, then try to pick a point, another point that is very further away from this point. In that way, you're utilizing more of the graph. Now suppose that if my slope, this gradient is also known as the slope of the graph, right? So suppose if there is no slope, meaning that the gradient of the graph is 0. Well, again, we are dealing with displacement time graphs. So suppose that this graph has a slope 0, which would just mean that it's any straight line, or you can say a line which is parallel to the x-axis. In this case, we can clearly see visually as well that there is no slope in this graph. The slope is 0. Which means if I take any 2 points on this line, because there is no change in the value of s, remember the slope was delta s by delta t, so there is no change in the value of delta s, which would keep upstairs 0 and downstairs whatever delta t do you have, it won't matter because this thing vanishes. And this means that whenever the gradient of a graph is 0 or the slope vanishes, implies that the velocity of the object is 0, whatever meters per second, but it doesn't matter because it's 0, which means that 0 slope implies the object is at rest. Now, if the slope is constant, as we saw over here, which means slope is only constant if the line is not curved, then the velocity will be a constant value. Then you could also have a case, let's go to the next page, where I could have an increasing slope. What does that mean? Well, I can draw a picture. Suppose that you have, this is your vertical axis and here is my horizontal axis. Again, here I have time, and on the vertical we have displacement measured in meters. Now, a slope that is increasing would look something like this, right? Now, in this case, we can clearly see, if we understand the meaning of slope, we note that the slope at this curve is a tangent at every point on this curve. So for example, I wanted a slope at this point. I'll just draw a tangent like this at this point, and it would be something like this, right? Suppose I want a slope at this point, then I'll draw a tangent line to this point, and it would be something like this. You can clearly see that this white line, this one, is less sloped to the horizontal axis compared to this green line. It has more slope. So what is really happening is, in this curve, as you move from the origin upwards on this curve, the slope is increasing. Now, when the slope is increasing, this means that that velocity of my object is increasing with time. So to find the velocity at any particular point on this graph, I'll have delta S divided by delta T, which would be, using limit, I'll say that delta T goes to 0, which means I'm trying to compute the instantaneous velocity. So I'll have to find a velocity at any particular instant, which means the instantaneous velocity. I'll just draw a tangent line to the graph at any relevant point, right? Whatever point I want to compute its velocity, and I'll calculate the gradient of this tangent. So for example, I wanted to compute the velocity at this white point, then I'll draw a tangent to this point, and I'll pick any coordinates. So I could pick this point, of course, because the tangent touches this point, and then I could pick any other point on this tangent and find the gradient of this tangent using the same way we did before. And then you would find the velocity of the object at this point where the tangent touches the graph. You can do the same thing with this green line, where if you want to find the velocity at this green point, then you'll draw a tangent to this green point, pick this green point and any other point on this green line, and find the gradient. That would give you the velocity of the object at this point, right? So at this value of t. So that's how you find the velocities or gradients when you have the increasing slope case. So when your velocity is increasing with time. Then we can also discuss the case of a decreasing slope, and the graph for a decreasing slope would look, now we know how would it look like. We can take a guess because we have enough knowledge. It should look something like, if this is t and this is displacement in meters, then decreasing slope should look something like this, right? Because, well, we can check, because if I have a point over here and I need the velocity, I'll use the same trick. I'll draw a tangent to this point and it would look something like this. And suppose now if I want a velocity at this point, then the tangent at this point looks something like this. And I can clearly see that the velocity in this case is really decreasing. Why? Because the slope is decreasing. I can see visually that here I have a slope which is comparatively higher to this slope from if I look at this horizontal axis, which means at this point the graph has a decreasing gradient, which would imply that the velocity is decreasing. Right. So let's quickly summarize displacement time graphs. So what we have studied so far, we know that if I have a displacement time graph and I need to see what is it telling you about velocity, then if this is displacement in meters and this is time in seconds, then we know that the increasing velocity, so I'll write it over here, increasing velocity is given as, or you can draw an increasing velocity graph as a graph whose slope is increasing. So it would look something like this, right? Now, in this case, the slope of the graph is increasing at every point. Hence, this is the increasing velocity. Suppose I need a graph where the velocity is constant. So a constant velocity graph would look something like, if I have t and s over here, then a constant velocity would mean that the displacement would be increasing, but the velocity is constant. So it's increasing at a constant rate, because remember, constant velocity implies that the displacement is changing with time, but at a constant rate. So that would look like a straight line between these two axes. So this is a constant velocity. At every point, the ratio between s and t is going to be the same at every point on this graph. Hence, the velocity is a constant value. Now, suppose that you have another one where you want to see what does it look like on a graph if I have zero velocity. We know zero velocity, right? So just give it a number 3. Zero velocity implies that there would be zero change in displacement per unit time. So there is no change in displacement. So if I was initially at this point, then after some time passes on this axis, I'd still be at this point, and then I'd still be at this point. So we can draw this line and we can see that at every time we are at a same value of displacement. So here the velocity is 0. Next, you can have a case of decreasing velocity. And we saw that if I have a case of decreasing velocity, which is case 4, and this is time, here we have displacement in meters, then the slope should be decreasing. And we know a decreasing slope would look something like this, because again, at every point, if I were to draw a tangent, the tangent would look something like this over this point. The tangent would look something like this at this point, and we can clearly see that this tangent is less compared to this one. So the slope really of this tangent is smaller compared to this one. Hence, the slope is decreasing as time passes. So this is a decreasing velocity graph.